These are the solutions to activity 4. Question 1, which compound is incorrectly named? So we have chloric acid, which is actually the incorrectly named, so this is wrong. Chloric acid is based off of chlorate, so this is chlorate. So chloric acid would be H plus adding in for a neutral compound to HClO3. That would be chloric acid. HClO4 is perchloric acid because perchlorate is HClO4 minus. So this HClO4 should be perchloric acid. So A is incorrectly named. Copper 1 sulfate is indeed Cu2SO4, so we have a 2 minus. So we have a plus 1 charged copper, which is indeed copper 1. Butane is C4H10, so 4 carbons, 3 bonds to hydrogen for the end positions, and then CH2s in the middle. Each carbon gets 4 bonds in the saturated hydrocarbon, so that's correctly named. And then K2HPO4 would indeed be potassium hydrogen phosphate. Hydrogen phosphate's HPO4 with a 2 minus charge, so what happens here is phosphate ion ordinarily would have a 3 plus charge. H plus neutralizes this charge down to a net minus 2. So the hydrogen phosphate ion is HPO4 with a 2 minus charge with K pluses. Neutralize that 2 minus with 2 K pluses. So K2HPO4 is indeed potassium hydrogen phosphate. So that's correctly named. So the right answer to number 1, the incorrectly named compound is HClO4, which is perchloric acid. Number 2, write the proper combustion reaction for the complete combustion of octane, C8H18. And then what is the coefficient in front of CO2 in this reaction? Okay, so we would have C8H18 reacting with O2 to form CO2 and water. The combustion reaction specifically formed these 2 combustion products. As written, we would have 9 here to put our hydrogens in the balance, but you can see this is going to give us a fraction for O2. So let's actually carry through with the fraction for O2. We'd have an 8 here. So we need 8 O2s for the oxygen and CO2. Then we would need 4.5. So we need 12.5 O2s ordinarily for a proper, the key word here is the proper balanced reaction would have no fractions. So I'm going to double all these coefficients. I'm going to go to 2, go to 25, go to 16, and then go to 18. Then we can double check. 16 plus 9 should be 25 O2s that we need to get the proper O's for both sides. So if we want to count them specifically, 16 plus 16, 32 plus 18 is 50. So just checking the O atoms, and then we get 25 times 2, 50 O's on both sides. 16 carbons and 36 hydrogens on both sides. So the coefficient in front of CO2 should be 16. Sulfur and fluorine react to form SF4. This is an example of what type of reaction. So we're combining 2 reactants into a single product. So this is the example of a combination reaction. If you imagine the opposite reaction, if you said, well, what about SF4 decomposing, or just said the reaction type, but if we had this reaction here, this would be a decomposition for just the opposite reaction. Question 4, what is the percent sodium in sodium carbonate? This is the percent by mass. I should probably say that to be a little bit more clear, but the percent sodium by mass in sodium carbonate would be 2 times the mass of sodium, which is about 23.00 atomic mass units. I'm going to divide by the formula weight of the compound. This will be my percent sodium. I need to multiply by 100%. So I'm basically saying for this compound here, how much of the mass is just due to sodium. The formula weight of sodium carbonate would be 23.00 times 2 plus 12.01 plus 3 times 16. So this formula weight here is 106.01. So 106.01. And then we just take 46.00 divided by 106.01. The percent sodium should be about 43.4%. Next question, which a mole of which substance contains the most total atoms? So if you think of like 1 mole of, say, carbon would equal an Avogadro's number of C atoms. But if you had 1 mole of, say, CH4, each molecule contains 5 atoms. This is going to contain 5 times an Avogadro's number of atoms. So this question is really just asking which of these compounds or substances has the most atoms. So here we have 8 for S8, and I have 5 times 3 for 15, plus 4 for 19 atoms per unit or per molecule for NH4, 3PO3. And then for Al2SO43, I only have 17. So I have 15 for 5 times 3 plus 2, 17 atoms per unit or molecule. The word unit is slightly more appropriate here because these are ionic compounds. They really don't exist as like a molecule unit. They exist as just like that collection of 2 aluminums, 3 sulfate ions, or 3 ammonium cations, and the phosphide ion. This compound here, an Al2SO43, these are both called ionic compounds. So because they're not molecular, they tend not to exist as a molecule, but that's just a minor detail. But the one that contains the most atoms is the substance that contains the most total atoms is the one that per mole or per unit contains the most total atoms. So 19 atoms, 1 mole of NH4PO3, NH43PO3 would contain 19 times an Avogadro's number of atoms. Answer C would be 17 times Avogadro's number, and A would be just 8 times Avogadro's number. How many grams of fluorine are contained in a 705 gram sample of SNF2? Number of grams of F. A few ways we can solve this. Let's do it this way. 705 grams of SNF2. Let's just use that for 1 mole of SNF2, but that's 156.7 grams. That's what this information here is meant to say, that the molar mass of the sample is of, not the molar mass, the molar mass of SNF2 is 156.7 grams per mole. So we're just using that grams per mole here. And then 1 mole, or excuse me, I flipped this. I mentioned in class that it's good to show your units. Here's a case where as long as I cancel out my units, I catch my mistake that I need to divide by the grams per mole of SNF2, and then 1 mole of SNF2 contains 2 moles of F, because there's 2 Fs, and then 1 mole of F is the atomic weight of F, which is 19.00. So 705 divided by 156.7 times 2. It's an important 2 here. 2 Fs per mole of SNF2 times 19. 170.96, so 171 grams. Now you could have also said, well, what's the percent? Got a 2 here, just writing in the SNF2. You could have also said, well, what's the percent F in SNF2, kind of like we did for sodium carbonate earlier, and just multiply this by the 705 grams. So that's another approach, would be, oh, just work out the percent F. So 2 times 19 divided by 156.7, and then multiply that by 705. Now, how many total fluorine atoms are present in that previous sample that we were working with? Well, we had 171 grams of F. Well, we can just use and go back to moles. And then 1 mole of F contains, not the L, so 1 mole of F would be 6.022 times 10 to the 23 F atoms. So just using Avogadro's number, 171 divided by 19.00 times 6.022 times 10 to the 23 is going to be 5.42 times 10 to the 24. When iron, well, that'd be 3 plus. So when iron 3 carbonate is heated, it decomposes in iron oxide and CO2. What is the coefficient in front of CO2 in the proper balance reaction? So we'd have Fe2CO3 3 reacting in this reaction to form, let's leave this blank for just a second, plus CO2. We're pulling CO2 off, and then we're leaving behind the oxide ion. So we leave behind the oxide ion, just like we had a CO3 2 minus, we leave O2 minus, so iron 3 plus. So we have iron 3 plus, oxide 2 minus, so Fe2O3. So we've just gone from having an FeCO3 to an FeO3, and then CO2 here, we're going to need 3 in front of CO2 to put everything into balance. And so 2 irons, 3 oxygens here, the other 6 oxygens here, and then our 3 carbons. So the coefficient in front of CO2 should be 3. What is the empirical formula of this mineral here with these masses? So I just start with a mass ratio that would be true for the sample. 34.6 grams of carbon are present in ratio to 30.4 grams of iron in ratio to 34.9 grams of sulfur. I like to think of these as just being ratios to each other, so I'm just kind of going from the gram to gram to gram ratio to the mole to mole to mole ratio, which is getting closer toward that simplest empirical formula. And so in terms of atomic weights for copper, 63.55 grams per mole of copper. Got to go to a periodic table for these. That's where I'm getting this from here. Then multiply by, for iron, 55.85. And then 32.06 grams per mole of sulfur. Let's stop and calculate how many moles we have in this sample to get our ratio of moles. So 34.6 divided by 63.55 is 0.5445. Present in ratio to 30.4 divided by 55.85 to pretty much the same number, 0.5443 moles of iron. So my copper and iron moles should be equal to each other, so I can kind of already start rolling out answers B and C. So their ratio should be the same as each other. And 34.9 divided by 32.06 is 1.089. So sulfur looks to be double. Let's just make sure. So let's divide all these by the smallest. I think we can see that 5445 and 5443, I mean, those are practically going to come out to be equal to 1. So about 1 mole of iron, I'm not worrying too much, or 1 mole of, this is copper, to 1 mole of iron. I'm not worrying a whole lot about sig figs because, when we get our empirical formula, we're really just trying to get 1 sig fig out. 1.089 divided by 0.54, I can see this is going to work out pretty well. That's 2. And so my formula should be Cu, Fe, S2. Should be answer D. So we find the empirical formula of a compound C3H4O, and we know it has a molecular weight through some other experiment of 336.4 AMU. What is the molecular formula of this compound? So we just need to find the number of multiples. I take my 336.4, and I'm going to divide this by the formula weight of the empirical formula. So I take my empirical formula weight My empirical formula weight is just 12.01 for the 3 carbons. So 12.01 times 3 plus 1.008 times 4 plus 16. So this formula weight here is 56.06 AMU. Now I should be able to divide this into that 336.4 number and get a whole number. The most likely reason I wouldn't get a whole number here is just a math error somewhere along the way. So I get 6, that's not 6 moles, it's just a ratio of 6. So the ratio I get here is these are both AMUs, so this is just a ratio of how many of the empirical units there are in the molecular formula. So now my formula should be C3H0. I just want to start C3H4O, and then I'm going to multiply each of these by 6. So C18, H24, O6. So P4 and O2 are reacting according to this reaction below. How many moles of P4, O10 form when the reaction completes? Well, there's a few ways to do this. I'm going to show it 2 ways. The BCA chart is not entirely my favorite way to solve this problem if I'm on a test, but it's a pretty good way, I think, to understand what's going on here. You have 2.5 moles of P4, so I'm just writing whatever P4 is, and underneath the O2, I write the 10 moles here. And then I have to get my reacting, I initially don't have any product either, so I'm tracking the product too. And then by the stoichiometric coefficients, I can write the following. I can say for every X that I lose off of P4, I lose 5X off of O, and then I gain X in the case of P4, O10. Okay, so one of these 2 values here goes to 0. So does it go to 0 here, or does it go to 0 there? And so to address that, just imagine we go to 0, let's say in the O2 column. Let's just pick it for a minute. Let's say we go to 0 here. What would X be equal to? We'd have 10 minus 5X is equal to 0. And so then X would be equal, we just solve for X, the 2.0. And so if X is 2.0, I lose 2.0 moles of the 2.5 moles of P4 that I have, and I'd be left with half a mole of P4. And when I see this, that half a mole of P4 is left, I know that this is my excess reactant. That's the amount that's present in excess. And that the reactant that's completely consumed is my limiting reactant. So the limiting reactant here is oxygen. Kind of got lucky, I just randomly picked it. Now imagine we did this problem and I randomly chose and said, well, what if we make our P4 go to 0? Then our 2.5 minus X would be equal to 0, so X would just be equal to 2.5 moles. And then when I do 10 minus 5 times 2.5 to work out how much oxygen would be left over, the answer would be like negative 2.5 moles. I would have consumed more than what I had available. So the BCA chart is just trying to say, well, what do you have before the reaction takes place? What's the change that's taking place? And what's present after? We can't go negative. The lowest you can go is 0. And so one of the 2 reactants goes to 0, if not both. It's possible if we just mix 2 moles and 10 moles, both of them would have gone to 0. But in this case here, oxygen's completely consumed, and then our X is 2 moles, so we're producing 2 moles of the P4O10. So we're making 2 moles of P4O10. Okay, now I mentioned I chose 2 ways to solve this problem. So an alternate method would have just been to say, well, how many moles of P4O10 can you make if you consume all of the oxygen? Let's consume all the P4 first. Let's say we consume 2.5 moles of P4. Then for every 1 mole of P4 that's produced, we would get 1 mole of P4O10. So that would be 2.5 moles. It would be 2.5 moles of P4 would form, P4O10. Now, how many moles would we form if we react all of the oxygen instead? So let's say we react all of the oxygen. For every 5 moles of oxygen, we get 1 mole of P4O10, and that would be 2.0 moles. Now, this way, sometimes we get numbers, and it's hard to remember, well, is the answer 2.5 or 2? Well, let's think about what this means. What this problem here is saying is if I react all the oxygen I have and it goes away, and we produce as much P4O10 as we can with that much O2, we get 2 moles. So at this point here, I've run out of oxygen. All my oxygen's gone. It's been converted into P4O10. Now, to get to 2.5 moles means I would need more oxygen present than what I have available. So you can calculate how many moles of product you would form, and then if you're trying to figure out which of the reactants the limiting reactant, it's the one that makes the least amount of product, and then the one that makes more product would be present in what we call the excess reactant. So some of the P4 would remain after the reaction completes. How much? Half a mole. So we could work out how much, of oxygen is consumed. We could work out how much of the P4 reacts with it. You can look at your reacting coefficients here and see, well, 2 moles of P4 would react with it. 2.5 moles are available. Half a mole remains. So good thought on stoichiometry problems will get us through them, and a majority of them, just by trying to think through what's going on with the reaction and how we can consider that reaction and quantifying the details, either through using dimensional analysis, setting up a chart, maybe a BCA chart. How many grams of HCl are produced in the reaction? 1.23 grams TiCl4 with excess water according to this reaction below. So if I react all of this with excess water, how much TiO2 do I get? Or sorry, how many grams of the HCl do we get? So the number of grams of HCl would be equal to, let's start with 1.23 grams of TiCl4. We want to use the molar mass of TiCl4. Titanium is 47.88. And then Cl is 35.45 times 4. So that's 189.68. 1 mole of TiCl4, according to our reaction, will produce 4 moles of HCl when it reacts. So this is going away. This is forming during the course of the reaction. And then 1 mole of HCl would be 36.46 grams. So I do the math here, 1.23 divide by 1.23 divide by 189.68 times 4 times 36.46. So I get 0.946 grams. 2 moles of iron, 6 moles of carbon reacted. The reaction yields 3.6 moles of iron. What's the percent yield of the reaction? Kind of like the first problem is or let's even go here. The percent yield of a reaction is just our actual yield divided by our theoretical yield or our maximum possible yield times 100%. This yield here is the one you get using stoichiometry. Just use your stoichiometry to figure out how much of the product we should be making here at most. And this is just one where we have to consider limiting risk excess reactants. This, like, when we give moles, it's pretty easy to be like, okay, we got 2 moles of this. For every 2 moles of this, we get 2 moles of iron. So if all of this reacts, we get 4 moles of iron. But what if all of the carbon reacts? For every 3 moles of carbon that react, we would produce 2 moles of iron. So that would be 6.5 divided by 3 times 2 for 4.33 moles. So for this given quantity, the most we can make of iron is at 4 moles. We've consumed all of the iron oxide at that point. And then if we wanted to get to 4.33, we just need to add more of our starting material. So our theoretical maximum yield from our stoichiometry would be 4 moles of iron. Should be formed during the course of this reaction. We formed 3.64. Your actual yield should be this yield or lower. Otherwise, we have some extra impurity that we're adding in with our iron oxide. So I do 3.64 divided by 4.00. I get 91% yield. Now, this is an example of a problem that's not covered this semester, so we can skip this one. Now, it's not entirely hard to think of a sample containing CHNO can produce CO2 and water. So I think we could solve this. It just might take a while. So when you see problems like this, just know they're not going to be on the test. But we just be trying to figure out how much carbon and CO2 comes from our sample. The carbon going to CO2, the hydrogen goes to water. And we get our oxygen atom by a simple difference. But again, we're skipping this problem this semester. I don't want to dwell on it too much. What is the formula of barium sulfate? The naming review, barium 2 plus, PO4 3 minus, so Ba3, PO4 2. And then finally, which formula does not represent a stable compound? I put this on here because I think this is a weird way of asking just which formula doesn't have usually like the right charge balance, the right count. So this is like trying to get us to figure out, well, which of these compounds just doesn't represent something that's supposed to be stable based upon the charges we know of. Chlorite's a minus, calcium's a 2 plus. So CaClO2 would be probably metastable. I want to be very stable with a minus charge. We'd want to get a second ClO2 for it to be stable. So B is the one here that should not represent a stable compound. A is sodium peroxide. If you can name the thing and it looks about right, we have the O2 2 minus ion, 2 pluses to balance the charge. This is sodium peroxide. C is rubidium phosphite, and D is sulfurous acid off sulfite. So sulfite is the 3 with the 2 minus, 4 with the 2 minus is sulfate. So H2SO3 is I hope I can spell right. So sulfurous, OUS, acid, and then rubidium phosphite for that one. That's all this activity. Thanks for the attention.